Alrighty, let's start off a few of these videos on linear regression here. The basic idea with linear regression, we got two actions going on. One, we're just trying to fit data, and if you want to think of it, so I've got some data here. Here's X, here's Y. It looks like a straight line trend. I would love to find this Y equals mx plus b curve. And so one aspect of it is just finding, hey, what are the best m and b? Now, what do we mean by best? Okay, and in this case, your linear regression is kind of taking the idea of predicting y values from x values, and it's making a basic assumption in the actual statistics part of this, and that is that for any given x value, that we have our model y equal mx plus b. Okay, that's the basics. That's going to give you sort of an average y, but then plus an error term. And what it assumes for that error is that you've got a normal distribution, okay, so a bell-shaped curve of varying values here, with a mean of 0. By having a mean of 0, then the y equal mx plus b is sort of the average value for any given x. So a mean of 0 and then some sort of variance, and it's the same all the way up. And so that's the statistical assumption of what's going on, and we'll look a little bit at the statistical aspects, but we're also just interested in the fit. And what it does is, by deciding what is the best fit, it is getting this deviation, this vertical deviation from the model, y equal mx plus b is the line, takes the point, okay, so it takes the actual point, say yi, and it subtracts the estimated point y hat I, like that, and it squares it. It sums it up for each one of these, and what it does, it minimizes that sum. Okay, so it tries to find the m and the b that will minimize this sum of squares of the deviations from this, and that's all it does. And we could solve something like this a few different ways. One is with calculus. Multivariate calculus. If I write this out right, it's minimize the sum, and well, yi, that's fixed, that's your data, minus, and then m times xi plus b. Well, the xi is fixed, so it's actually m and b. And so you'd sum this, say I equals 1 to n for your n data. So really this is a function of two variables, m and b, and you could take partial derivatives, set things equal to 0, solve for m and b. There are actually a little bit better ways to do this. Those are linear algebra. So another way to view this is that I want to find an m and a b, right, that I want m times x1 plus b to equal y1. Well, you give me x1 and y1, I can find all kinds of m and b's that would do that. Oh, well, an m times x2 plus b equals y2. Oh, two equations, two unknowns. The unknowns are m and b, and I could tell you what those are. I could solve those and tell you m and b, but oh, bummer. Typically, we have more data than we have unknowns, right? We still don't know m and b, but we have at least 3 data or 4 data or 10,000 data or something like that. You know, so this would go down here to mxn plus b equals yn. Well, we would never expect to be able to find a solution to these n equations with just 2 unknowns. Okay, no solution would exist. But this can be written as a matrix problem. We could get a matrix that looked like x and a 1 and a x2 here and a 1 and so forth, all the way down to xn and 1. And if that multiplies an mb like that, equals, and then our y1, y2, and so forth. And hey, if you haven't had the linear algebra and matrix notation, don't worry about it. It's not. We're not really working with that. I'm just pointing out that you could get this, and then it turns out if I write that as a, and I'm gonna, well, I'll use P for parameters, I guess. AP equals Y, like that. So I've got this matrix times that. Then actually it turns out that if you can't solve this problem, there's no solution. But it turns out if you multiply by A transpose on both sides, what you get is a 2 by 2 matrix system, which is really just a system of 2 equations, 2 unknowns, a linear system of 2 equations, 2 unknowns, and you can solve this. And when you solve this, you get m and b. It's awesome. Okay, so to me, much simpler than the whole idea of the taking derivatives and so forth. Although, it turns out you get the same exact equations, and that's why you get the same m and b. So linear algebra or multivariate calculus, either one will get you there and get you answers. And then even within linear algebra, there are other ways, actually better computational ways to solve this problem. But somehow or other, we can get a solution, and we'll just use technology to get that solution, to find the minimum of those sums of the model. So here's our model, and how much our data deviate from the model. That's all this is summing up. There's our data, there's our model. How much do they deviate? We're going to square that and sum it up. We could use absolute value. Square turns out to be nicer, and so we'll square each of those deviations, sum them up, and try to find the minimum. Okay. And again, that's all that the model fitting part is doing. Now, when we do that, what happens is we'll get estimates. Okay, we'll get estimates, m hat and b hat. And along with those estimates, we'll get standard errors. Okay, standard errors. And for us, again, so this is standard error of m, and we got a standard error for b. We're not going to dive into this sort of stuff greatly, but what we do care about is from these two things we can estimate some confidence intervals, and we'll look at that in another video, but confidence intervals. And for the most part, as long as we have a decent sized data set. Now, how decent size? Well, say n is greater than or equal to 30. Okay, if we have a data set that big, then what we can do is we can say the real m, and usually we're mostly interested in the slope, but sometimes we're interested in the intercept. But the real m, if we look at it as an element of our estimated m minus 2 standard errors, and then m plus 2 standard errors. Okay, now again, this is all based on the normal distribution, that sort of thing. But not 90. If we go with the multiplier of 2, that's a very bad writing there, we have a 95% chance that the real m is inside that interval. So that's pretty good. And so we can get these confidence intervals. If we get the m and its standard error, we can get these confidence intervals on, well, what do we think the real slope probably is? And a lot of it can, a lot of what matters here is whether or not, from a statistical standpoint, whether or not this interval contains 0. If it contains 0, then, I might go with the notion that, well, the slope is 0. That's kind of from a statistical standpoint, that's what it's trying to look at. Okay, so we can put our data into technology. We can generate an m hat and a b hat, and when we do that, depending on the technology we're using, we can probably get a standard error on those, and then we could create these confidence intervals. We could do the same thing with b, plus or minus 2 of these. And again, if we've got any kind of decent sample size, 2 is a good number. If it's a smaller sample, like n equals 10 or 12 or something, 20 even, it's not quite as close a rule of thumb, but you could just bump it up to 2.5 instead of 2 for that multiplier, and that would work fine. Okay, but if we, again, if we've got a decent size data set, then this 95% confidence interval, as we call it, we just go plus or minus 2 standard errors on each side of our estimate, and we figure the real answer is probably in there somewhere 95% of the time. Okay, now the other thing that we look at with least squares is called the R-squared, and what that's looking at is, again, remember that we're adding up these variations here. All right, so we've got this sum of the yi minus the y hat I squared. We're adding all those up. Well, if we look at that difference compared to the overall variation, where if we took the sum of each of our yi values minus y bar, okay, the average of the y values squared. If we look at that ratio, that is our r squared. And so what we're looking at here is of this total variation, okay, here is explained by the model. Okay, so if we, oh, I might have to come back to this because yeah, okay, so actually it's, I believe it's 1 minus this. I don't have notes in front of me right now, so I believe it would be 1 minus this would be our r squared. So actually this yi minus the y bar, the reason I realized 1 minus is if things were perfect, right, if our data were all along the line, then this answer here, right, these would be perfect, so that would be 0. We would get a 0 up here. And so I should change that to not explained by the model. Sorry. But then if we take 1 minus that, then that's our r squared. Okay, so if the model was perfect, this part would be 0. And on the other hand, if the model is totally bogus, okay, so suppose I have data that look like this, and I would generate that line. Well, actually, I can tell you that line is at y bar. And so what would happen is this model would be the same as y bar, and so we would get basically yi minus y bar, quantity squared summed up over yi minus y bar, quantity squared summed up, and so that would be a 1, so it's 1 minus that. Okay, so our r squared is 1 minus this ratio of deviations, and so what r squared does is it gives us in the end here. So when you see the r squared, this is the percentage or percent of the variation in y explained by the model. Okay, so again, I screwed that up at the beginning of it, but so these variations, right, here's the model, there's the actual data, so as I add up those variations, that's not explained by the model, okay, and so we get that ratio and take 1 minus that. So, if we don't do the 1 minus, if we take that part out of there, we get the percentage that's, or the ratio that's not explained by the model. So 1 minus that will be the percentage that is explained by the model. And again, if the model, if there was no slope and so forth, then the model would just be flat like this, and the data would be this way, and actually this line would be at y bar, and that is because actually you can do a pretty good job of eyeballing the least squares line if you get x bar and y bar, because what the right answer, you can reduce this actually back here, this calculus problem or the linear algebra problem, you can actually reduce this to a problem of one variable and m, because, well, if you know, because what we know is the right answer is y equals m times x minus x bar plus y bar. Okay, so the right answer contains that point. So if you have a bunch of data, then maybe right there is the point x bar y bar. Okay, average of the x's, average of the y's, and then the correct answer is going to go through like that. So I actually know a point on the line, I just need to get the slope. And so you can do a reasonable job of, if you've got pretty good data that are reasonably tight together, not too much variation, then you can compute, x bar, y bar, those averages, and then just mess with m until you think you've got a pretty good slope that fits your data. About as many above as below, that kind of thing. Okay, so we're going to be interested in the parameters m and b, and again, though, b not a big deal. If I know the slope, if you tell me the slope, because I know the line contains x bar, y bar, b is not a big deal. I can get that, right? Y bar minus m times x bar. B equals y bar minus m times x bar. And so the key is finding that slope m. And so that's one thing we want to do, and we can look at the standard error and so forth to get an idea of, might that slope actually just be 0? And then we can also get an idea of how well the model fits the data with this r squared term that we want to look at. And again, the r squared, all you're doing is you're taking the deviations from the model, squared of course, but and then dividing those by the overall deviations from the mean of the y values, and that gives us a percentage not explained by the model. And then if we take 1 minus that, or 100% minus that, we get the percentage that is explained by the model. And so that r squared, which most programs that do the data fitting and so forth spit out, it's nice to know, and we'll use that to compare models. We'll use r squared and something called adjusted r squared. Okay, so that's the beginnings of linear regression.